Hello all, today we are covering 8.1, but before we get to that, I have this similarity in right triangles discovery sheet to help us understand what is going on in today's lesson. So the first thing I want to tell you is that we are trying to solve for the missing variables, and it looks like a hodgepodge of stuff. We would like to try to use Pythagorean theorem because we see there's 90s and such, but unfortunately we don't have enough information to do that. So I'm going to take a look here. I'm going to give you a little hint. We have some similar triangles, obviously, similarity in right triangles. So we have a 90, we have a 65. We know the third angle in the smallest triangle must make those add to 180, so that's 25. Then we know this is a 90 here, which means this other side must be 65. Angle here is also 90, and this guy down here is 25. So notice we do have the angle-angle similarity. We actually have all three angles similar, as we know will happen. So that means we can set up some proportions. So you'll notice down here, instead of having all three triangles together, I put them all so they were rotated nice and relabeled everything, so that way I could solve a little easier with better visuals. I am going to go ahead and write out which triangles are similar to what though. So I know triangle ABD is similar to triangle BCD is similar to triangle ACB. Notice I went from the 65 to the 25 to the 90 each time. Okay? Now the similarity statement can help us set up a proportions. We don't necessarily have to use that though, because I have them nicely laid out for us. If we didn't have them nicely laid out, it would probably be beneficial to do that. So now, the hardest thing that we need to do is match up pieces so that we can actually solve for the variables. So notice there's an x here and an x here. These are really the same shared x between the small triangle and the medium triangle, but we can use them to solve. So in that triangle, notice I'm solving for x. I want corresponding pieces, so I'm going to need to use this 4 and this 6 as well. So if I'm going to solve for x, I can say 4 over x equals x over 6. I cross multiply. X squared equals 24. So our solution is x equals the square root of 24. Now we will be simplifying radicals now instead of making them a decimal all the time. I'll give you a quick rundown of that. So to simplify a radical, you just find all the primes. So we know 2 is a prime that goes into 24. And I keep just breaking them down into primes. I like to call this a factor tree. I highlight all the leaves on the ends of my branches, all my primes. And then because this is a square root, I am looking for groups of 2. So I have one group of 2 2's, so they come out, and I get the square root of, and then 2 times 3 is 6. So 2 times the square root of 6 is what x equals if you wanted a decimal approximation, which you will be asked for sometimes, but sometimes you'll ask for a simplification. That is about 4.9. Okay? We can also solve for other things. Let me shrink this down. Notice we're still just using our proportions idea. We are not yet leaving that behind. So if we solve for y, notice there's a y in this triangle too. And then we want the corresponding pieces. So we'll have 4 over y equals y over 10. We'll do this once again, cross multiply. Y squared equals 40. So we have y is the square root of 40. Now notice once again, we need to check to see if this reduces. So I'm going to use my prime factor tree, circle my leaves, highlight my leaves. I have square root of 2 times 2 times 2 times 5. Look for groups of 2. So I have 2 root 10 is what y equals. If you were asked for a decimal approximation, simply plug that into the calculator, and that is about 6.32. And then lastly, we solve for z's. Notice I want to find where my z's are, so I can solve for them. Actually, since I have x and y solved for in other spots, I could use different triangles now, but that's not necessarily helpful. I mean, it could be, but I mean, might as well solve the way we have been. So we have z's in these two, which means we need corresponding parts. Oops. This guy. My bad. So we need these ones. So we have, let's see, z over 6 equals 10 over z. Cross multiply. Z squared equals 60. Take the square root. Do your prime factor tree. Highlight your leaves. Look for groups of 2. So we get 2 square root of 15, which is approximately 7.75. That makes good sense, because the square root of 64 is 8. So we have our 3 solutions. So that's just kind of our intro. We're using similar triangles to set up and solve proportions. Now if we pull up 8.1 and get started, we have something called the geometric mean. The geometric mean of two positive numbers a and b is the number x, such that notice how it looks exactly like how we solved it. We have x's multiplied by each other and then two numbers, getting us the same thing that we had before. So the geometric mean of 9 and 4 is 6. Because 9 times 4 is 36, we take the square root of that and we get 6. So find the geometric mean of 2 and 5. Basically what you do is you say, well, x squared equals 2 times 5. If you notice we have the equation up here, x squared equals a times b. Take the square root, 2 times 15. My bad. So the geometric mean of 2 and 50 is 10. Okay, you could also set up a proportion if you wanted, but you're going to get the same thing when you cross multiply. Okay, then we're going to do another geometric mean. Same thing here. You can say x squared equals 3 times 12. X squared equals 36. Take the square root of that, and x is going to equal 6. Okay, once again, you could have set up a proportion. So look, this guy looks a lot like our intro. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. If you recall, we had 65 degrees and 25 degrees and 90 degrees, meaning we have angle similarity, and that the smaller two triangles are similar to the big triangle. And that's going to happen if you have right triangles with an altitude dropping down to the hypotenuse every single time. So write a similarity statement identifying the three similar triangles in the figure. Notice we did this earlier. We had 65 here, 25 here, 65 here, 25. Sometimes it's nice giving like arbitrary numbers like that when you know you have 90s. So that way you can match up what angle goes to what angle. In this case, I'm going to go 65, 25, 90. So EFH is similar to triangle. FG GH is similar to triangle, the whole big one, EGF. Okay? So I finish with 90 every time, the 25 degrees in my middle, and the 65 is my first one. So write a similarity statement identifying the three similar triangles in the figure. Once again, you can give some arbitrary numbers. You can say this is 30, that means this has to be 60. That has to be 30, this has to be 60. Let's match them up. We have some 90s here and a 90 here. So L and M would be 30, 60, 90. So let's check the next one. 90. Oh wait. Yeah. 60, 30, 90. So this doesn't work, not in the same order. NML, 60, 90, 30. LOM, that would not work either. That's 30, 90, 60. LMN, 30, 90, 60. LOM, 30, 90, 60. And MON, 30, 90, 60. This one looks pretty good. Maybe we'll check the last one just to make sure. The last one, L, MN, 30, 90, 60, L, O, MO, 30, 60, 90. So nope. C is our good one. Those are the similar triangles. It's almost easier to just write them yourself. So we can use a geometric mean. So right triangle geometric mean theorems. So geometric mean altitude theorem states the altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. The length of the altitude is the geometric mean between the lengths of these two segments. So we have an altitude dropping down in a right angle. We can either set up our proportions like we had before, or we can see that the hypotenuse is equal to the geometric mean of the two sides, or segments that it cuts it into. So x times y is equal to h squared, or h equals the square root of x times y. And then we have geometric mean leg theorem. So this is when we have an altitude. This is when we're looking at the legs. The altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. The length of a leg of this the length of the leg of this triangle is the geometric mean between the length of the hypotenuse and the segments of the hypotenuse adjacent to that leg. So if CD is the altitude to hypotenuse AB at the right, then C over B equals B over X. Or the leg equals X times C all squares to the square root. Or other leg, C over A equals A over Y. Or if you take the leg, not the hypotenuse, the leg, equals the square root of Y times C. Now that one I think is a little more abstract. Notice it's just setting up proportions as if we had the similar triangles from the very beginning of the slide. So if we find C, D, and E, we could try to set up some similarities, see if we have enough information to set up proportions like that. Or we can go ahead and use our geometric mean altitude theorem and geometric mean leg theorem. So I'm going to skip and not do the proportion. I'm just going to go straight for the geometric mean altitude theorem. First I need to know this whole length. If I'm going to use the altitude, notice it is the altitude equals the two pieces that split up that are square rooted. So the altitude, E, equals the square root of the two smaller pieces. 6 times 24. 6 times 24 is 144. Oh, that's really nice. The square root of 144 is equal to 12. Okay? Now you can do the geometric leg theorem. So we have that the leg equals the square root. If we take a look, leg equals the square root of the small piece of its own triangle over the whole side. So the small piece times the whole side. 6 times 30 is 180. I don't think that one turns out quite as well. We'll check and see though. Nope, not quite. So this is approximately 13.42. But if it asks for a perfect square root, we take the factor trees. Oops. Then find groups of 2. If you have 2 things to pull out, you take 2 times 3 is 6. Root 5. So 6 root 5 is actually also equivalent to 13.42. Just a reduced version of square root of 180. Okay? Then we also need to solve for C. C is equal to the geometric mean of its own side 24 times the whole thing. So 24 times 30 is equal to 720. The square root of 720 is also not a perfect square. It's about 26.83. If you are asked to find the reduced form though, you want to be able to do that. So this one's actually quite long. So you'll notice my factor tree got pretty big. You want to give yourself ample workspace for that. So we have 2 times 2 times 2 times 2 times 5 times 3 times 3. Find groups of 2. Pull them out front if we can. So 2 times 2 times 3 should be 12, I do believe. So 12 root 5 is actually equivalent to the square root of 720. All right, so there's C, here's D, and here's E. If you wanted to, you could have solved for C using Pythagorean theorem and went on your merry way, okay? So find E to the nearest hundredth. We're going to use geometric mean leg theorem. So we have E equals its own piece over the whole thing. So the square root of 16 times 20. Now this one I do believe we are just going to make into a decimal, or maybe it's a whole number, we'll see. 16 times 20 is 320. And I get that that is approximately 17.9. It's technically 17.8885, rounds up to 17.9, so C. And you could have actually went ahead and just done Pythagorean theorem, because we do have a 90. We have the legs as well of the medium triangle. Okay? A jetliner has a wingspan BD of 211 feet. The segment drawn from the front of the plane to the tail, AC intersects BD at point E. If AE is 163 feet, what is the length of the aircraft to the nearest tenth of a foot? So I'm going to go ahead and move some information in where I can see it more clearly. I know AE is 163. I also know that BE is half of 211 at 105.5 feet. From here, I have an altitude coming in, and I have part of the hypotenuse broken out. I need to find this other piece here. Okay? So what I'm going to do is I'm going to use the geometric mean altitude theorem, where my altitude, 105.5, equals the square root of the two pieces of the hypotenuse that it's cutting. So I take 163 times x. To get rid of the square root, though, I need to take both sides squared. So 105.5 squared is 11,130.25. That now equals, because these cancel out, 163x. Divide by 163. And we get that part is 68.28 feet. Now, there is an answer of that. The thing is, that is only this question mark. And we want the length of the aircraft. So we just take 68.3 plus 163, and we get that the answer is 231.3 feet. Okay, so B is our solution. Your homework for today is page 541, problems 1 through 4 and 11 through 14. And I am going to have you guys write all the square root answers as decimals today. Don't worry about simplifying the square roots yet. We'll discuss that a little more later. Have a great day.